building an afternoon like this around, we can build around the Connects cards. We're not necessarily going to do the specific activities. It's going to be pretty. Some of it's going to be pretty similar to those activities, but I'm maybe probing some different concepts, slightly different concepts, and talking about it maybe in a deeper way, having you talk about it in a deeper way than you might do with your students. So yeah, it's definitely not. This is not sort of a how-to use this kit kind of session. We're going to talk about the physics around this kind of system. I also want to point out this book that just got handed out. One of the ways that I can help, we set up sort of a schedule here, particular activities, A, B, C, D, what we're going to do today. But part of the way I can help in this program in general is if you have questions about particular things you're doing in the classroom, ask me. If you want, you go through the book. There's a particular part of the physics of that, the concepts of energy, maybe chemistry that you're not comfortable with. I can try to help to the degree that I understand it. I can help you. All right. So what we're talking about today, or what we're exploring again today, is forces in motion. Hold on 1 second. I have to admit I'm a little bit addicted to PowerPoint, which is really not a very good way of teaching things, but it keeps me on track. So one of the things that, so what we're diving back into, last time we had an afternoon session we talked about Newton's laws. And so we're going to kind of go back through these again. Let's talk more about them. And if you have lingering questions about Newton's laws and how to apply them, this is this session, that's part of the point. We're going to do some new activities, but we're kind of going back over the same material and looking at it from a different perspective, okay? So let's remind ourselves what Newton's laws are. There's sort of 3 laws. There's the law of inertia. And this is something that really came up a lot last time, is to really get your head around what inertia is. One of the things that kept coming up was this confusion between, well, this idea, is inertia a force? Okay, which is, I think, what I found is that was something that you all were tending to think of it as. And we want to explore that and try to get you comfortable with the idea that inertia is not a force. It's actually what opposes a force. It's the property of a mass, of an object that resists motion when a force is being applied to it. And Newton's second law is the law that relates forces to motion. Okay? The second law is really the law that of most physicists, when they do their work, they're relating the forces and the motions, where we can write down what we call equations of motion to determine where an object's going to go based on the forces. And Newton's third law is action and reaction. When one thing presses on another, that other thing presses back on first. Okay? So these are the 3 laws of motion that we talked about last time. Let's remind ourselves what this first law of motion really means. An object at rest tends to stay at rest unless acted on by an outside force. I mean, this is really how you want to think about inertia. Inertia is, we use inertia in everyday language, even when we're not talking about masses, right? It's a tendency of something to want to stay the way it is, either stopped or moving. Okay? And so when we're talking about it in mechanics, what inertia is, the more inertia an object has, it's really, so mass and inertia are really the same thing. You kind of want to think of them as the same thing. The more massive an object is, the more inertia it has. Okay? So one of the things that we also have to remember is that an object that's moving at a constant velocity, unless there's forces acting on it, it's going to continue moving at a constant velocity. Okay? All right, so this is what we're kind of dealing with today in more detail. It's Newton's second law. And you saw the slide, a lot of these slides we had last time. And Charlie and I were just talking about this. I'm putting an equation up here, and in some ways, it's more important that we get the conceptual aspects of this. But it's hard for me. I'm limited in my ability to talk about this without putting an equation up. That's just because of the way I think about this. But the way that force and motion are related is through this equation that Newton sort of determined. which relates force to mass and acceleration. And so one of the other things that we want to talk about today is really get you comfortable with the idea of acceleration. What exactly is acceleration? What exactly is force? And what exactly is inertia? All right? So a force accelerates a mass. Okay, here's one of the things I want to talk about. When we say force, so let me make sure everybody's comfortable with what I've written here. F is force, M is mass, A is acceleration. Okay? So what's acceleration? Who can tell me what acceleration is? What is acceleration?
A change in speed over time.
That's pretty good. Change in speed. Change in speed. Only. So let's remind ourselves some of the things we talked about last time. Let's talk about speed and velocity. One of the things we talk about,
velocity has direction.
Yeah. Very good.
Change in velocity over time.
Right. One of the things that Linda just said that's really important, and I think is really powerful, is to be comfortable with the language you're using when you're talking about these concepts. Okay. And that's important to teach students too. So, and that's why I totally agree with what Linda said. Writing and speaking about these concepts is as important as being able to, write equations down. I often get students, and I bet Charlie will agree, you can get students who are very brilliant mathematically, who can get problems absolutely correct, like crazy complicated problems, and you ask them the most basic question about physics in terms of just answer this question in just normal language, and they'll get it wrong because they don't really understand deeply, because they don't really speak about it. Okay? So speaking about physics or the chemistry or energy in the proper way is really an important thing. And I'm not saying that to chastise you. I mean, I'm saying it that it's good to get to talk about it, and it's good to talk about the physics.
Is speed like a physics term at all, or you really only use velocity?
No, speed is what is on your speedometer. So if you think about it in your car, what is that gauge telling you? Is it telling you direction? What's that?
It's telling you how fast you're going.
Yeah, this is what formally it's telling you. It's telling you your speed, but it's not really interested in, it doesn't care about direction. Okay? So that's still a useful property to know, the speed of something. But there's something more that tells you a little bit more, and that's velocity. Velocity is the speed and the direction. Okay? And the fancy word we use in physics for this kind of thing is a vector. It's a vector because it has direction. Some properties don't have direction. Mass doesn't have direction. Volume doesn't have direction. But some properties do, like velocity, or like a force is a vector. It has an amount and a direction. Okay. So acceleration. Acceleration. I'm a very loud speller. Acceleration is the change in velocity per unit time. It's the rate of change of the velocity. Okay?
Which also includes going slower as well as deceleration.
Right. So you can either use the language deceleration. I think it's okay. It's all right to use the word deceleration, or you can also think of it as a negative acceleration.
Negative. That's what I was looking for. Negative acceleration. But I could say negative acceleration.
Okay. So that's what acceleration means. All right. And we'll keep working on that. We're not gonna walk away from it. We're gonna keep thinking about this. But one of the things I wanted to make sure because I think this is part of where that confusion comes from. When we put equals up there, we say force equals mass times acceleration. That does not mean it is. It means that this thing is equal quantitatively to this thing. They're totally different things. They're not. So this inertia is not a force. Okay? Let me explain what I mean in more detail. It does not mean it's not is. Okay? The way of thinking about this is on this side of the equation, you have all the forces on the object. Okay? So this is the forces. So the way you want to think about it is think about the object first. You have an object, a ball, a car, a chair, a table. You want to know how it moves. All right? So the first thing you're interested in is that object. That's the blue thing in that equation. You're interested in how it moves. That's the red thing. That's the motion. And how you determine its motion comes from understanding what forces are on that object. Okay? Here's another way of looking at it. This may be a more intuitive way of looking at it. I've just rearranged the equation. Okay? I've written down the equation a slightly different way. I've brought the force, I've brought mass underneath force. I've divided both sides by mass. So what this says is the acceleration, how much the object accelerates, is equal to the force divided by the mass. So now maybe it's a little more intuitive now, because what you're saying is the larger the mass is, the less it accelerates. All right. Right, so if you have a humongous number down here, let's say you have some force, you pull on an object with some